All right, can you all hear me?
Yes.
Okay, cool. All right, so let's get started. Some reminders. So your first exam was graded. The average was 68, which is fine. I did not count one outlier on the exam. I still got a grade. I actually have to grade one more exam, so I don't think it's going to make that big of a change to the average. So I was trying to get things back to you by Monday. I almost made it. I think I got done like midnight or something. So anyway, that was the average, and I gave you guys the exam distribution, and I showed you the standard deviation, so you get an idea of how things break down in terms of, if you're one standard deviation or half a standard deviation from this, or 1.5 standard deviation from the score. Okay. Oh, that doesn't reflect the overall class grade, because I'm going to do your final grade is going to be based on your overall course grade. The curve will be based on your overall course grade. Okay, but at least gives you an idea kind of how you did in the class. 68 is pretty much fairly average. I was going to also give you guys the key last night, but so I scanned my key, and then I realized I scanned the same page twice, so I didn't send it. So probably by this evening you'll get the key to the exam back. So once you look at the key, if you have any questions, let me know. Okay. We're going to be talking about how to calculate an electric field, and so I have a worksheet on Canvas for you to do. It's called the electric field worksheet, and that'll be due on the 21st. It's basically, I tried to set it up so that you go step by step through the process of calculating electric fields, and that way you can see where you get stuck. Because a lot of students have difficulty in calculating electric fields for continuous distributions. It's going to be very similar to what you did in Physics 205 when you calculated gravitational fields. You're going to replace the masses with charge. Okay. Today I want to continue my discussion on electric fields. Does anybody have any questions before I get started? No questions? Everybody's okay? Go ahead, Chase, you have a tiny question. Are you having a hard time hearing me? Oh, I think I know. I think I know what's wrong. Hold on a second. Something got unplugged. Can you hear me better now? Okay, sorry, something got unplugged. So, regarding the homework, that's supposed to be microcoulombs, Chase, and I'm using an old version of the problem. That's why that A comes up. Okay, but Chase, that's supposed to be microcoulombs. That A is just, that shouldn't be there, because that was an old version. Other questions? And everybody can hear me okay, because I had a problem on Thursday. My audio and my video, at least the video I used with my camera, the audio disappeared after about 20 minutes. However, the audio for the video that's on Zoom is fine, or on Confer Zoom, that's fine. So last Thursday's video was kind of messed up. Sorry about that. Okay.
I actually had a question on the second homework problem. For part B, I was wondering what the conducting wire, what that would change in the how you would solve it.
Well, it allows electrons to flow from one object to the next. It's the same thing as if you would touch them together.
Oh, okay. So they would So the electrons would like balance out on each of them?
If they're the same, were they the same size? Yes. They balance out each one of them. And also, it makes the problem easier if the conductors are far apart. If you use a wire and you keep the wires far, you make it long. When the conductors are far apart, it's easier to do the calculation. When you have a conductor, the charges, because they're free to move, the problem gets very complicated when you have two conductors that are real close to each other. Because what you'll get is an asymmetric distribution of charge. You'll have more charge here and here and less charge on the ends. Of course, that depends on what the sign of the charges are here. So with the wire, you keep them far apart, and you don't have to worry about the asymmetry and the charge distribution on each of the conductors.
So that's what the equilibrium thing means. It's like it means the charges are balanced out.
Yeah, I got to be careful about that. It really doesn't mean the charges are balanced. It means that the field inside the wire is 0.
Oh, okay.
Okay. So Kai, we're going to be finishing up chapter. I forget the section number because they're on the syllabus. But we're finishing up chapter 23 today, and we're going to start on chapter 24 tomorrow on Gauss's law. Okay. So last time I introduced the concept of the electric field, and oops, dropping everything. Let me just say a few things just as a review. We also talked about Coulomb's law, but I'll go with what I finished off with. We defined the magnitude of the electric field. Or actually, let me do it this way. The electric field is the force per unit charge experienced on a test charge. That's called a test charge. We call it a test charge because we're going to assume that it's small enough so that the charge doesn't affect the electric field produced by whatever charge distribution you have. Yes, and I changed the homework date to the 19th, Nico. It just didn't show up on Canvas. Okay, let me continue here. So it's the force per unit charge. This is the test charge. We assume that it's small enough so that it doesn't affect the field due to the rest of the charge distribution. If we have a point charge, we can write the electric field as K, Q, this is the source of the field, over R squared times R hat. If I write, for example, if I have this is my source of the field, and this is a point in space. This is a point in space. It's not a charge here, okay? Because everybody gets mixed up with this. This is a point in space. Then the field at this point, due to the source, is given by this expression. R hat is a unit vector that is directed from the source of the field to point P. This R squared is the magnitude, the square of the magnitude that goes from the source to the point P. So maybe I can do this, put a subscript P, because this represents the fact that the vector points from the source to point P. And I got this equation from Coulomb's law. This is the equation for an electric field due to a point charge. The magnitude of this is given by that expression. And we also said, at the end of class, we established the fact that the electric field is directed away from a positive charge and towards a negative charge. Okay, so these are things we've established the other day. Remember that this came from Coulomb's law. I just took a force between two charges and I divided by Q, where I assumed one of the charges was a test charge. Why is this field concept important? Well, it turns out that this equation, or writing this as F, the force on a charge Q, is equal to Q times E. This is actually more general than Coulomb's law. It works in every case. Coulomb's law doesn't work in every case. That one does. Because Coulomb's law does not work in a case where a charge experiences a force in the absence of other charges near it. Because you can have time-varying magnetic fields producing electric fields, and they're going to produce a force on a charged particle. Coulomb's law does not, cannot explain that effect. It's not valid in that case, but this is valid in every case. You can use the electric field, for example, to say the following. Let's say I have just a distribution of charges, a whole bunch of them. It can be continuous distribution, or it can be a discrete distribution of charges. And I want to find the field at point P. Okay, I can say, what is the field at point P due to the distribution of charges? But then if I put a charge here, Q, this guy is going to experience a force due to that field. I don't have to say this charge over here is going to experience a force due to all these charges. I can replace the idea of a whole bunch of charges with the idea of electric field. The electric field sets up a condition in space that characterizes it. The electric field sets up a condition in space that defines an arrow in every location in space, a vector. It has magnitude and direction. Okay, so when you take a test charge, when you take a source charge, when you take a source of a field, it could be a positive charge, negative charge, it could be a plate that's charged, or it can be a sphere that's charged, whatever it is. If I put something here, it's a source of a field, then I have to assign everywhere in space that's near this charge a vector. There's a unique vector at every location in space that's represented by the fact that there's this charge here. So what you've done is you put a charge in this region of space, you've distorted the space around it. In fact, you've distorted space and time. If you want to think relativistically, you've distorted space and time because you have to assign a new vector in every location in space here, meaning that if I take a charge and put it here, it's going to experience a force at that location. This is an abstract concept. Now, the electric field also acts as an intermediary agent, just like the gravitational field. The electric field reconciles the fact that Newton's third law is not always valid. If I have a set of charges in space, and I have another charge here. Let's say something happens to this one. There's a force acting on it. Something bumps into Q2. The force on this one the force on this charge is far away from Q1, Q2, and Q3, obviously will change because this charge has moved. Could be I bumped into it, it could, however this thing moves, the force on this one's going to change. But how fast is it going to, how long does it take for the force, or let me rephrase that, how long does it take for Q to feel the effect that Q2 moved? Is it instantaneous or does it take time? If I bump Q2, let's say, or I move Q2 from here to here in a short period of time, will Q experience that change right away? That's my question. Will Q experience the change right away? No, Q will not experience it right away. So that means that if Q2 moved from this location here to this location because of a force, the dp dt of Q2 is not going to be equal to dp over dt of Q. That means that the time rate of change in momentum is not going to be the same. That means Newton's third law is not valid. So where's that missing change in momentum? It's carried by the field. The field carries that information. If Q2 goes from this location to this location because of a force, the time rate of change in momentum on Q2 is not going to be the same as the time change in momentum on Q1. Newton's third law is not valid, so where's the missing momentum? It's carried, the information is carried by the field. Because the electric field carries energy and momentum. In fact, the electric field will carry energy, linear momentum, and angular momentum. This is why this idea is important. Of course, it also allows us to be able to solve other problems, okay? Okay. And let me find my cursor. So, what I want to do now is do a couple of examples where we calculate the electric field due to charge distributions. First one will be a discrete charge distribution, and then the second will be a continuous charge distribution. I also have a problem which I videoed. So I'm not going to do it in class. I'll show you the problem, and I videotaped it. So what I'm going to do is to maybe catch up a little bit in terms of time. I'll have you watch the video. I still have to caption it. I'll give you the link to the video. Okay, I'll send you the YouTube link to the video. All right. Okay, so let's say I have three charges. One here, and one here. Let's say, call this Q1, Q2, Q3. So this forms a right triangle, for example. And I want to calculate the electric field at this point due to these two. Okay? Basically, it's a problem of linear superposition. It's a problem where I have to add vectors. And that's it, really. It's kind of like the force problem, except that I'm dealing with an electric field. So what do I do? Well, first of all, if I want to find the field at this point due to these two charges, let me get rid of this charge here. Let me call this a point in space. I want to find the field at this point due to these two charges. Let's say, let's make this positive and let's make this negative. We've established the fact that the electric field is directed away from a positive charge. So then I know the field due to this positive charge is going to be away from the positive charge, and it's going to point towards that point. We've established the fact that the field, due to a negative charge, points towards a negative charge. So basically I have two arrows, one in the x direction, one in the y direction. All I have to do is use this equation for a point charge. To find the magnitude of this guy and the magnitude of this guy. Break the vectors into components. Well, in this case, it's easy. Okay. Sum the x components, sum the y components. Use the Pythagorean Theorem to find the resultant vector, at least the magnitude of the resultant vector, and then take the inverse tangent of the y component over the x component to get the angle. Same thing as we did for the Coulomb's law problem, except we're dealing with the letter E instead of a letter F. Okay? So this is a very physical way to do it because we established the fact that the field points away from a positive charge and towards a negative charge. And now I'll make this more concrete in a minute. Now there's a second method, and I'm going to show you the second method. And the reason why I want to show you the second method is so that we get used to using the vector r hat. We got to get used to using this vector r hat. So I'm going to do this. I'm going to do the same example using two different methods so you get to see how it works. Okay? Using this method, all you have to do is calculate this and then write down the unit vector that goes from the source to the point in each case. And then sum the two vectors in IJ notation. When we do the continuous charge distributions, that's what we're going to do. So let's do this problem that you see before you. I'm going to replace this bottom charge with a negative 3.00 nanocoulombs. So this is going to be wrong. I'm going to replace this one with a plus 6.00 nanocoulomb. Remember, 1 nanocoulomb is 10 to the minus 9 coulombs. Let me get rid of the arrow. And eventually I'll put a 5 nanocoulomb charge here, but let's pretend it's not there for now because the 5 nanocoulomb charge is not going to contribute to the field at that point. Okay, so since this is a negative charge, the field due to this charge at point X is going to point towards the charge because it's negative. Electric fields are directed towards negative charges and they point away from positive charges.
Wait, so if the point is on top of or like in the same space as a charge, then it doesn't contribute to the field at that point?
Correct.
Oh, because the R would be 0?
Yeah, it's a little more complicated than that, but it's tough to do with point particles. It's a little bit easier to see with, if I had a sphere and you wanted to find the field at the center of a sphere, you can easily show that it's 0. There's no charge there too. It's hard to deal with this particular one because a point charge is not real, okay? So I don't know if you did in Physics 205, you calculated the gravitational field inside the Earth. Did you do that? And so at the center it's 0, right? There's no mass. There's no mass at the center, so there's no field. So it's kind of the same idea, except that it's hard to visualize that or hard to conceptualize that with a point particle. Okay.
Oh, okay.
And there's ways, and when you learn a little bit more math, there's a way to deal with that. You write a weird function to take that into account. I don't want to get into that. Okay, so I know that the field due to this one. So maybe I should label some things, huh? Call one and the other one number 2. I'm going to be consistent with my notes so I mess up. Let me call this E6 because of this guy, and this E3. Is that okay? Let's calculate the magnitude of E6. I'm using this top equation up here. I'll put the units again this time. And one thing I forgot to mention are the units on this thing. And then I'm going to divide by the distance. The distance from here to here, what is that distance? Is 0.3 meters. And if you do the calculation, you will get minus 600 and the unit is a Newton per coulomb because the meter square will cancel. One of the coulombs will cancel with this, and so I'm going to get, oops, I calculated the magnitude, 600 newtons per coulomb, but it's going to point to the left. Let's do E3. E3 is going to be 8.99 times 10 to the 9th. Three times 10 to the minus 9 coulombs over when you work this through, you'll get 2,700 newtons per coulomb. And of course, this points down, that points to the left. So all I have to do now, well, I have to resolve these into x and y components, but this has no y component, that has no x component. So if I write this as a vector, I would write it this way. And then I have to add those two vectors. Then I use the Pythagorean Theorem, right? I use the Pythagorean Theorem to get the magnitude. I didn't put the minus sign in because when you square a minus sign, you get a positive sign. You get 2770. That's the magnitude. How do I get the angle? It's the inverse tangent. Now be careful, both of these are negative. The y component over the x component. Is the calculator going to tell me the truth when I get the answer? What quadrant is this force in? I'm sorry. What quadrant is this vector in?
The third?
It's in the third, so the calculator is going to lie to me, so I got to add 180. And so the angle I'll get is, if I'll get 257 degrees. From the positive x-axis. Okay, now let me do it the other method. Let me do it using the other method. We already know the magnitudes and stuff. The other way is to do it this way, is to do the following. And I'm going to use a different color. And let me know if it's hard to see this color. I'll use purple. So the equation, the vector equation, is k q over r squared r hat, where r hat is a unit vector that points from the source to this point. So this vector points in the minus which direction is that? The minus I hat, sorry. Points in the minus I hat direction. So I'm going to write the unit vector in purple. From the source to the point. From the source to the point. Notice, this is not the direction of the field. This is the direction of the unit vector. Okay, I'll say that again. This is not the direction of the field. This is the direction of the unit vector. Notice that it points up here. Even though the field, the y component of the field points down. But don't worry about it because that's going to work out okay. Because when I do the calculation, E6 is going to be 8.99 times 10 to the 9. I'm not going to put the units in because I'm going to run out of space. Times here I'm going to put the sign in of the charge. So that's E6. E3 here I'm going to put the sign of the charge in. And this is going to be the j hat. This will come out to minus 2700. This will come out to minus 600. You get the same thing. You still get the same components. Personally, I think doing it this way is less physical, but when we do the problems involving continuous distribution, this is the way we're going to do it because there's too many things to sum over. Questions on this?
I have a question.
Go ahead.
Why is R3 positive j hat? Why does it point up instead of down like in the last problem? Yeah, and that was a point I was trying to make. It's why I changed colors, because what am I drawing in this case as opposed to the previous case? In the previous case, I drew an arrow that pointed down. What did that represent? The field. What does this represent? So the unit vector to the point we're trying to get to. Correct. So that's the difference. So where does the minus sign come in? It comes in from the sign of the charge. Okay, thank you. Yeah, and that's important. That's always a point of confusion when we do these problems. You know, why the heck did he change the direction? Because doing it this method, you're doing it more, to me, this is less physical. The first method is way more physical.
okay? Because we established what the direction of the field should be. This is not physical at all, but you can still use this method. It's to me, it's more mathematical than physical. It'll work, but it gives you no physical intuition. But when we start doing the continuous distribution problems, we're going to have to kind of use this method because we can't sum things individually. We have to do an integral. That's why. Okay, that's the problem. Okay, so if you have discrete charge distributions, I really recommend that you do it the first way. And then I'm going to give you a link to several videos. I've been trying to caption one of them, but it takes me a long time to caption them. I'll give you the YouTube links. So I did a Coulomb's law problem the other day, and I said there's a second method you can do it, which is based on this. And I have a video for that too, so you can watch it. And you can see it's way less physical. You don't develop any intuition in the problem, but it works. And again, I show it to you because we're going to be doing problems where we have to understand what this unit vector means. Okay. All right, so let's try these questions. Suppose I have a rectangle. Let's see how fast I can solve this one. I have a rectangle with the charges shown. Let me draw in my charges. If it doesn't look like a rectangle, it's supposed to look like a rectangle, okay? I want to find a field at that point P, some location in space. Okay? Due to those 4 charges. So I'm going to do it the physical way, because if I do it the mathematical way, it's going to take me forever to do it. This is why I like doing a problem the more intuitive way, even though the other method does exist. So at this point, the electric field due to, this is right at the center of the rectangle, by the way. The electric field due to the negative charge points towards the negative charge. Points towards the negative charge. These point away from the positive charge, so they got to be this way. And it's along the line joining the point P and the charge. Those arrows represent the electric field due to each of those 4 point charges. Now, what can I say about the electric field at the center? I claim that the electric field at the center points straight down. The reason why I claim that is because of the fact that all these distances are the same. Remember, okay, all these R's are the same, all the Q's are the same, well, I mean, the directions are the same. And then all these angles are the same. So realistically, if I break these up into components, I have one down, one to the right, another one down, this one, I'm sorry, that's to the left. This is to the right. Then I have this one, and this one, and this one. I'm backwards, don't I?
Professor?
Yes.
I understand why it's like both down because of like the charge in the top and in the bottom. But earlier you were saying something like how just like with gravity at the very center, there's like no gravitational like force or something, and like no electric force or something like that. So like in the center, why is there one? I guess.
Well, that's a different point I was making, right? Because what I was asked was, does a charge produce a field at its location? So if I put a charge here, does it produce a field at that location? My answer is no, because that is the same idea as finding the field at the center of the Earth, which is 0. There's no mass there, right?
Yes.
Okay, so it's the same idea, although the reasoning, the mathematics behind it is a bit more complicated. Okay, so that's different from this, because this is just a location in space. P is a location in space. P is not a location of a charge. Second of all, we're determining the field at this point due to the charges that are not at that location.
Okay, that makes sense.
Okay. All right. So everybody see that these x components cancel and these x components cancel, and then the 4 y components add together. So let's say I figure out this angle, whatever that angle was, and I can do it. Then my answer, my electric field, would be this. Let's call this B, and let's call this A. Okay. I'm done. Because I use symmetry for my I use symmetry arguments. I drew the arrows. I said that the arrows will cancel because the angles are all the same and these distances are all the same. Don't just, yeah, in a test, by the way, if you want to use symmetry, don't just say, oh, they cancel because of symmetry. Show me the symmetry. Okay? But then I get the answer right away. That's my answer. And of course, I can write theta in terms of A and B if I wanted to. I'm just being lazy. Are we okay with that? Here's another one. A ring.
Wait, why is that -4?
There's 4 of these, right?
Yeah.
1, 2, 3, 4 y components. Each one contributes the same.
Yeah.
So that's why I put a 4 there. And they all point down.
Why is it negative?
Well, don't the arrows point down?
Oh, yeah.
Okay. Based on, you know, how we establish what the fields look like, right? The fields always point towards the negative charge and they point away from the positive charge.
Oh, okay.
Okay. But see how fast you can do some of these problems? What if I have a ring of charge? A uniform distribution of charge all the way around the ring, and I'm right at the center. This is, again, this is a location in space. This is not the location of a charge. I have a meter that measures electric fields, and I bring the meter right there. What's it going to read? What do you think? What do you think it's going to read over there?
I think it'd be 0.
Yeah, it's going to read 0. Why? Because let's say I pick, the charge is uniformly distributed. So if I pick this little piece of the ring and one on the opposite side, then if this is positive, if this is a positive little piece, then the field's going to point like this. And if this is a positive piece, the field's going to point like that. I can make that argument all the way around the ring. They're all going to cancel out. That makes sense? However, if I'm out of the plane of the ring, if I'm, let's say, over here where the tip of my marker is the location, then the answer won't be 0 because you'll have a component along the z direction that contributes. All the components in the plane will be 0, but the component in the z direction will contribute at the tip of my marker. I'm trying to center it. I'm trying to center it with this thing. It's kind of hard to do. Okay? So we can use symmetry arguments to make problems a little bit easier. Just say what they are.
Oh, wait, Professor?
Yeah.
In the denominator, should it be b over 2 squared minus q over 2 squared, or no?
Well, it's a hypotenuse, right? This hypotenuse. A over 2, b over 2.
Yeah.
Right. That has to be a plus. Right. We're not using. I mean, this is b over 2. That's a over 2. That's gonna be the hypotenuse.
Oh wait, you're wanting the green arrow, right?
No, I want the r is the distance from the charge to the point. So it's the purple arrow.
Okay, never mind. My bad. Okay. I'm sorry.
Okay. So now that we've done discrete charge distribution, this is where the fun comes in, is to do continuous charge distribution. Okay, and of course we're going to do problems that have symmetry, and we're going to do problems that are doable, at least analytically. I mean, even if they're not doable analytically, you can still do them on a computer. It just takes a little bit more work. So suppose I have some arbitrary distribution of charge in space, and I want to find the field. I want to determine the field at this point P. I'm going to put an X there because everybody, if I put a dot there, everybody thinks it's a charge. There's no charge here. I have an electric field meter, and I bring it at this point, and I want to determine, I want to see what the meter is going to say. It's the same thing as me calculating what the field is going to be at point P. So using this equation is not going to be of much use because R changes continuously, right? Because over here, I have one R hat, and then over here, I have another R hat. They're all different. In fact, if I break this up into many pieces, I'm going to have many R hats, right? So what do? I have to break up that object into many tiny pieces. I'm going to make my Q small enough so that these are the same over the size of that piece. Okay, I'll say that again. I want to break up my charge, whatever that is. It could be a sphere, a cylinder, whatever it is. I got to break it up into teeny tiny pieces, small enough so that over that piece, the R's are the same value. Then once I've broken up into pieces and I've determined an equation that represents the electric field for each one of those two pieces, I have to add them all together. I mean, really, that's what I've been doing with the discrete charge distribution. But then here, you have a continuous charge distribution. And for a continuous charge distribution, every one of these pieces is infinitesimally big. If I sum a bunch of infinitesimals, what does that become?
An integral.
A what?
Integral.
An integral. So we're going to be integrating. So our first goal is to write an expression for the contribution of one of these pieces to the total electric field. So I have to break my Q into dQs. And I got to write an expression for R squared for each one of those. And then I got to write an expression for R hat. So the goal here is to write an expression for R hat, write an expression for R squared, and then write an expression for dQ. Once I have that, then I'd integrate. And in this class, you're basically going to be given problems you can integrate. So Chase, Generally, on an exam, I'll probably give you integrals that you can do. Okay, I'm not going to give you a horrendous integral. I mean, if you can do it by substitution or whatever, that's fine. But if I'm not going to give you something, or if you could do by parts, yeah, because there's some that are really nasty. Okay, and I won't give you the nasty ones. If it was an in-class exam and I give you a nasty one, I either would just have you set up the integral and not integrate it, or then, yeah, I would give you a table. Okay, so what do you think is more important, setting up the integral or evaluating it? What is more important? Yeah, setting it up. And guess which is the hard part? Yeah, the setting up is actually the hard part. You guys all know the integration techniques already. You already had Calc 2, right? You guys know all that already. You probably can do a lot more difficult integrals than I can, because I don't do them very often. But really setting them up is where the key is. Okay? And that's actually kind of challenging at the beginning, because we have to learn how to write what dq is. Well, let me take a minute or two to say something about setting this up. If you look at homework problem number 9, I purposely created homework problem number 9 for you to practice how to set up a dq. Almost every problem, any problem you'll get either on the exam or in the homework, will be based pretty much on number 9. I mean, there might be one I missed, but I give you number 9 so that you can learn how to set up the integral. I shouldn't say every single one, but most of the types of problems you will encounter are similar to what you would get in number 9 in the homework. Okay, so problem number 9 is just a thing of setting up a dq. And if you had 205, Aviva might have had you do something like that with a dm. At least a worksheet. So what do I mean by this? So, suppose I have, let's think one dimension. Suppose I had a line of charge, one-dimensional world. Okay? Yeah, variable densities, those are fun, right? And I want to write down the amount of charge in that thing. Okay? So let's pretend, well, I'm just going to write it as charge per unit length. This is going to be, this length is dx. So my dq is going to be my charge density times the length of this piece, dx. And if I integrate my dq, that's going to give me q. Okay? So in one dimension, we use the Greek letter lambda. Now, if it's 2 dimensions, I mean, it's 2 dimensions, we're dealing with a surface. So if I have a ring of, not a ring, but a disk,
Wait, is dx the charge density, or is that...
No, dx is the length of this piece.
Oh, okay.
dq is the charge. Lambda is a charge density. So charge density times length is going to give you charge. If you add up all the pieces that make this up, in other words, if you sum your lambda dq's, dx's, from I equals 1 to infinity, of course, you know what that's supposed to be, right? That gives you your total charge.
Okay, cool.
Okay. So if you have something two-dimensional like a disk, what you have to do is imagine. Well, you got to be careful. The disk is really a double integral if you've had Calc 3, but I'm not allowed to give you double integrals. I can only give you things that vary with r. I can only give you things where the charge stays the same over all angles. So for example, if I take this disk and I break it up into a bunch of rings, the thickness of the ring is dr. Okay. This distance is always the same. So I can break this up so that all the way around the ring, I have the same charge density. In fact, the charge is evenly distributed over this whole ring. If I can take a pair of scissors and cut this out and straighten it out, its thickness would be dr, its length would be the circumference of that circle. What would be its area? Length times width, right? And so then my dq for this piece is going to be, again, charge density times dA. We use the Greek letter sigma for two-dimensional charge density. If you have a sphere, something three-dimensional, how would you break up the sphere so that you can write a dq? Well, again, I can only give you things that depend on r, not on angle. Because if I give you something that depends on angle, then it's a three-dimensional integral.
Cross-sectional slices of the area?
I'm sorry?
Would you use cross-sectional slices of the area? Like
yeah, you could, but then you would have to still do two integrals to do that. What you would do is spherical shells, like an onion. You know how an onion has a bunch of layers?
Professor?
Yeah.
Are you okay with us using double integrals if we know how to?
Well, I kind of would like for you to do it this way. You might make a mistake. That's the concern. I mean, obviously the double integrals are easy, but you might end up making a mistake. Because I'm showing you how to do it with doing it with single integrals. So in three dimensions, you would, like a sphere, you would break it up into spherical shells, much like you would, like an onion would look like. Just think of an onion with an infinite number of layers. The surface area, so for a sphere, each sphere has surface area 2 pi r squared, but then they all have a thickness dr. If you integrate that, you get 4/3 pi r cubed. So then your dq is your volume density times your element of volume. And so you look at problem number 9 on the homework, it has you go through an exercise where you're dealing with this. And so you want to use that as your guide to do problems going on from here, because we're going to do this in Unit 3 again. Yeah, there's two parts of it that's hard. It's this and then determining r hat. Okay. If the density is not constant, you have to integrate. That's what you got to remember. Why do they have to be perfectly circular? No, in fact, if you're talking about an electron, it's a wave. That has particle-like properties. When you talk about the electron in an atom, you can't just say there's this thing circling around the nucleus. It's actually a charge cloud around the nucleus. You can't tell where it's at any time. Really, you don't know where it's at until it hits something. Then you know it's there. That's quantum physics, though we don't want to get into quantum physics. Okay, so I want to do an example. So here's my, again, when these problems are a little bit more mathematical, I try to give you an algorithm. And so this is my algorithm that you want to use. And the worksheet that's due on the 21st has you go through step by step using this algorithm. One of them is an easier problem. The other one's a little bit harder on the worksheet. Choose a coordinate system. Write an expression for your dq. Determine r squared. This one's not that hard. And see if you can use symmetry to figure out which components cancel. Determine r hat. And don't include the components that are going to contribute. They're not going to contribute. It's not worth it. Put your equation together and then integrate. And see if your answer makes sense. So I'm going to do one example here. And I have a video of another one that I would like for you to see. Okay? Because they both take a little bit of time. But at least you have two examples. So here's my example. It's actually a three-dimensional problem. I actually picked one that's kind of hard. So I have a ring of charge, and we're going to make the charge distribution uniform, so the integration is going to be, this integration is going to be really easy. The setup is the hard part. You'll see what happens in this particular example. So I have a ring of charge, uniformly charged, and I want to find the electric field at some point P along the axis of this ring, but above the plane of the ring. We know that the answer is going to be 0 at the center of the ring. So my goal then is to go step by step and figure out this term, this term, and this term. And we've already talked about the ring problem, so we know, we kind of have an idea what's going to happen. Okay, so my dq, how am I going to determine my dq for this particular example? I got to take the ring and break it up into pieces. Why do I have to break it up into pieces? Because my unit vector r hat changes directions. Okay, so what's dq? Well, it's going to be, it's a ring, right? It's just a ring. It's a ring of radius a. And so it's going to be a lambda d something. How can I break up the ring into small pieces? Let me check that. How can I break up the ring into small pieces?
Smaller rings? Or?
Well, it's empty at the inside, just a ring. It's not a disk. Arcs. How big of an arc? How small an arc, I guess? Arc lengths, right? What's arc length? Do you remember the equation for arc length?
Radius times angle.
Radius times what?
Angle.
Angle, okay. So r delta theta, right? So I got to break this up into little arc lengths. I'll call ds. And this angle is d theta. if you want to call it theta, whatever you want to call it. And so my d something is a ds. Is lambda. My r here is my a. If I know the total charge, and I know the charge is distributed uniformly, then isn't it true that lambda is q over 2 pi a? Charge over length. The length is the circumference of the circle. And here, you want to see if this is correct? Integrate this. What does that give you? Does that give you Q?
Mm-hmm.
Then I know I'm right. Okay, so that's my dq. Okay? So what about our r squared? I want to do that one because it's easier. Let me write some terms here. So dq what about this thing? What is that going to be? Well, okay, this is going to be hard for me to draw. That's why I did it in PowerPoint. I want the distance from here to an element of charge. This distance is A, this distance is Z. What is this going to be? Yeah, Pythagorean Theorem. And I got to square it because this is squared. So here's I think this is going to be the hard part, r hat. R hat is the unit vector, right? R hat is the unit vector that points from the source to the point. So r hat is this guy. R hat is a unit vector. It has an I hat component. It has a, that's not an I, that's a J, sorry. A j hat component and a k hat component. Okay? And this is the, we're going to write, this is the angle alpha. The z component is easy. Okay? So you have a vector that points like this. This is the angle theta. This is the z component. So this is adjacent to the angles, that's cosine. But what about these two? What am I going to do about those two terms? What did I say? We talked about this problem. What did I say about the electric field in the plane of the ring at the center? Right, you have a component of the electric field. Let me get a black marker, which somehow disappeared from me. Here we go. So consider a component of the electric field this way and a component this way. What are these going to do inside the plane? They're going to be zero. So these terms are not going to contribute at all. If you wanted to do the math, if you like suffering, then you can actually do this, and it would look like something like this. Where phi is an angle that's measured in the plane. We don't have to worry about these because you'll get zero. Okay, when you integrate this guy and this guy over 2 pi, you're going to get 0. So all you have to worry about is this. You only have to worry about this term because you know the x and y components cancel. Thank goodness. Because otherwise we'd be in trouble. Well, it'd be more work. So I'm going to say that r hat something plus cosine alpha k hat. And I don't care about these terms. I'm only interested in the terms that are going to survive when I integrate. I know from intuition that only the z component will contribute. The electric field will point in the z direction. I know that.
Professor?
Yeah.
I can see how the I hat ones cancel out, and it makes sense how like only the k hat will contribute to that. But could you show how the j hat charge will cancel?
The I and j hat are in this plane, right?
Oh, right, that's right.
So these two will cancel out. The k hat is out of the plane. That's the one that survives.
Okay, yeah, that makes sense. My bad.
Okay, we have everything then. All we got to do is put it together. Oh, I can write, because I know that this distance and I know that distance, I can write it this way. All right, I can write it that way, which is what I wrote on the slide. So let's put it all together and carry out the integration. This is going to give you a good idea why it's all in the setup. dE, so there's going to be k, dq, divided by this thing, times the surviving component, I better be careful. Let me rewrite this. Okay, so now I got to integrate this over theta. How hard is that integral going to be?
Wait, why is that h hat and not
That's
j
a k.
hat?
I'm sorry. I don't make
Or
good.
k hat.
Right, because it's in the z direction, right?
Oh yeah.
Right. Those are supposed to be k's. I'm sorry if they're not. They don't look like k's. So when I integrate this, I get a 2 pi that comes out. I'll write it like this, so it's easier to see. That's it. If you were really far away from that ring, what shape, what would it look like? What would it look like if you're real far away?
A point charge.
Yeah, it looked like a point charge, right? So what if z is big? If z is much, much bigger than a, then I can ignore the a, right? So I get isn't this the field due to a point charge?
Mm-hmm.
Okay, so it looks like a point charge. When you're far away, it looks like a point charge. And it works. Now, what if lambda was not uniform? What if lambda depended on theta? Well, then I would have a problem. Then I would have to have my lambda here, right? Let's say lambda was this.
Is that capital Q, doesn't that represent like the total charge?
Correct.
Of the, oh, okay.
Yeah, that's correct. So if lambda depended on angle, then you'd have a cosine theta in here. That's a bad choice, actually. Let me make a cosine squared theta. Because if I made a cosine theta, the answer would be 0. Okay, and then you'd have to integrate cosine squared from 0 to 2 pi. And then the equation does show that the field is 0 at the origin, because if you put 0 here, right, if you put 0 here, you get 0 for the electric field, which agrees with what we said before. All this checks out, it makes sense. So when you get these, you should look at what happens when what the field looks like far away. Because far away should look like a point charge. And you should get the field to a point charge. Okay? So go over this one. I'm not going to make a video of this particular one because, I mean, this is usually a classic example I do. But this other one that you see in the slide, I made a video on it. And just in the interest of time, let me show you this. In the interest of time, I made a videotape. So I would like for you to watch the video. I'll send you the links. Okay, I'll send you the links tonight. You want to see this video because I actually do things, I actually look at what happens when you're really far away. And I go to this one in more detail. And in this one, the lambda is not uniform. Okay, and then on Thursday, what my expectation is that you're going to ask me questions on this. Okay. All right, so I'm going to take a couple more minutes and talk about the motion of a charge in an electric field. Okay, I might go a couple minutes over, I apologize. I'm going to do kinematics. Okay, so let's say we have a charged particle in a uniform field. Uniform, what does uniform mean? What do I mean by uniform? Anybody want to guess what uniform means?
The field does not change magnitude and direction.
Yeah, with respect to space, right? It has the same value in space. So that means because we can use uniform and we use the term constant. So when we talk about electric fields that are uniform, it means that same magnitude and direction everywhere. When we say it's constant, the electric field is independent of time. Okay? So when we say constant, we mean independent of time. That's really what we should say, what I should say. Sometimes I do get them mixed up. When we say it's uniform, it has the same value everywhere. So let's say you have a uniform electric field. So you have a charged particle and you look for an electric field. The only force acting on the charge is the electric field. And according to Newton's second law, it's ma. So A is Q E over m. So that means the acceleration is constant. So uniform electric field implies uniform A. Or a constant A, I guess we can say. So can you think of an example? I mean, use an analog that you learned from Physics 205 that would represent that. Can you think of an analog in 205 that would represent a constant acceleration?
Gravity.
Gravity, right? You guys did gravity problems, you did projectile problems. Every projectile problem you use, you can replace g with this acceleration. Okay? So, since, that's bad on my part, since a is dv over dt, then v is going to be the integral of q e over m dt. Okay, which is going to give you q e over m times t plus v naught. And if you integrate again, because v is dr dt, then r is q e over m t squared plus, or is that 1/2? You get the same kinematic equations you had in Physics 205, except in 205 this was a g, right?
Professor?
Yes.
Can you shift the camera a bit to the right?
Oh, you can't see that? Sorry. Yeah, something happened to the picture. Okay, is that better?
Yes.
Okay. So this is your kinematic equation from Physics 205, and then if you want to calculate the work done, so you got to calculate the work done. Let me go F dot dr. The work kinetic energy theorem says is this is going to be equal to delta K. And if E is uniform, then this is going to end up being Q E dot delta R, whatever that displacement is. Okay, so everything that you learned in Physics 205 applies here. Just the letters change. But I will tell you this, people have such a hard time doing these projectile problems. Okay, and you shouldn't. If I tell you I have, let's say I get 2 plates and I design the system so that the electric field points downward and is constant. Okay, let's let the electric field point downward and it's constant. And then I launch an object, a charge, horizontally in the x direction. What's going to happen to it as it goes into the electric field? Let's say this is positive. I should say this is positive Q. This is negative on this side. So the electric field points downward. What's going to happen? The field is uniform, so that means the acceleration is the same. See, and that's my point. Everybody has such a hard time with this because nobody's answered the question right away. If I take an object, I put it on a table, and slide it off the table, what's it going to do? If I slide an object off a table, I launch an object horizontally off a table, what's it going to do? What's the trajectory? What shape is the trajectory?
Parabola.
A what?
A parabola?
Parabola. What shape do you think this is going to be?
A parabola?
Yeah. Is gravity pointing down? I'm sorry. Is the electric field pointing downward here? Is the force pointing downward here?
No.
Yeah, it's pointing downward. This is a positive charge. This is going to do this. Same thing as if I threw something. It's the same problem. There's no difference. If I say you're replacing G with this thing, then the physics is the same. So you would have the same behavior as an object is thrown in physics 205. And people have such a difficult time visualizing this. And I've always wondered why. So me throwing an object across the room is the same thing as a charged particle going an electric field that points downward. It's like gravity. Gravity points downward. Obviously, if I made this negatively charged, it would go upward, but that would be very weird. Okay, because with electric fields, you can make particles go all kind of different directions. With gravity, particles want to go downward. Questions? Because everyone's quiet now when I ask these.
I have a question.
Go ahead.
It is about the term, the uniform and constant. So does the constant term mean that the electric field can change direction?
Yeah, I mean, you have to say uniform and constant. You have to say them both.
Okay.
Yeah, if you say the field is uniform and constant, that means it doesn't change direction all over, everywhere in space, and it has the same value, magnitude and direction everywhere in space, independent of time.
Then isn't saying uniform enough for us?
Well, you can have a field that looks like this. Right? Everywhere in space, it'll have that same value at t equals 1 seconds.
Okay, I get it. Okay.
Okay.
Yeah.
Yeah, Chase, if the parabola becomes upright, then this would have to be a negatively charged particle. Okay, so one of the things you want to go over is the kinematics from physics 205, projectile problems, because you'll see in the homework you'll have several projectile problems. And, you know, from my experience, students have a hard time when you replace the gravitational field, you replace the letter G with these 3 letters. Even though everything else is the same. Okay. Think of mathematically the form, but this equation has the same form as acceleration to the equation for acceleration to the gravity. Same mathematical form. These letters, only this set of letters are different. Okay. All right, I'm going to stop here. So next time I will do an example. I'll do an example of one of these, and then I'm gonna do Gauss's law. I'm gonna talk about field lines and do Gauss's law, which is interesting topic. I'll just say that. Okay. Any questions?
I have a question.
Okay.
On the board, what was the reason you gave when you wrote the delta R vector?
That's just a displacement. I mean,
no, like I think you said that something is constant.
Oh, the electric field.
Okay.
So you can pull the electric field out of the integral.
Mm-hmm.
Right?
Yeah.
I mean, you can, in other words, you can pull this out, and so then you end up like that, which is delta R. You know, it's your displacement because it's because work is forced through a displacement.
Yes. Mm-hmm.
Okay. I just wrote it as delta R. Sometimes it's written as S.
Yeah. I just forgot what you said there.
Okay.
Yeah. Thank you.
Sure. Other questions? And yes, this stuff is abstract. Regarding the first lab, what if you have no foam, styrofoam? Well, it says in the lab that you could use saran wrap. And I think I mentioned in lab, you can use saran wrap. You can use transparencies. You don't have any, do you have paper plates, Jacob? Oh, yeah, so saran wrap is fine. Saran wrap, you know, kind of is a little bit hard to work with sometimes, but if you can just lay it out flat that first time, it'll be fine. Anything else? All right, so Thursday in lab, I'm going to talk about, well, we're going to get ready for multimeter labs. So I have to talk about circuits already. So I'm actually going to lecture out of chapter 27. It's an easy chapter. It's way easier than the stuff we're discussing now. And there is, if you want to see some funny videos regarding electric circuits, there is this person online. He goes by, I'll put it in the chat. And he has videos on circuits. So he goes by this, his videos are called Electro Boom. And if you just search that, you'll find his videos on YouTube. And he has a lot of videos on electronics. How he'll talk about current, voltage, using multimeters, things like that. We also have a video on how to use a multimeter too. But anyway, Thursday lab, I'll talk about chapter 27. Okay, it's a pretty easy chapter. All right, I'm going to end it here. So you guys have a good evening. I'll be in office hours tomorrow night and work on your homework assignments.